All right, so Robert and I are talking about this question off of a practice test, which says we're looking at y double prime minus 7y prime plus 12y equals 0, and we're supposed to kind of classify this as a spring, or think about this as a spring and classify it. And so when I look at this thing, I'm thinking to myself, okay, there's an associated equation to this thing. That's r squared minus 7r plus 12.
Yep.
And this is going to equal 0. And then I need to find some solutions for this. And so maybe I do, oh, I don't know. Let's see, things that multiply to 12 and add to 7. Maybe
3 and 4.
3 and 4. Yeah, so maybe r minus 3 times r minus 4.
Yep.
Okay, check. Cool. So I got r is 3 and r is 4 are my solutions. And so my general solution to this equation happens to also be the homogeneous solution, right? And it's some constant a e to the 3t plus b e to the 4t.
So are you writing this down on any sort of whiteboard? Because I don't see one.
Oh, I am. I dropped the link into the Discord, into the general differential equations channel, I think. Okay, so technical difficulties straightened. All right, so I've got my homogeneous solution, right, which is my solution in this case, and it's a e to the 3t plus b e to the 4t. And so there's some things I can do without getting to there. Looking over here at which roots I have here 2 real roots, right?
Yes.
And so that means I'm in the kind of overdamped type of spring. But the fact that the real values I have are bigger than 0, right, tells me that this thing tends to infinity as t tends to infinity.
Okay.
Right? And so that means that my spring system looks something like this. It starts at some value and goes like that. Okay, so that doesn't feel like overdamping, because overdamping looks like this.
Yes.
Okay, so what is this thing if it's not overdamped? It's kind of the opposite of overdamped, right?
Yeah.
So it's anti-overdamped.
Okay.
Alternatively, it's not a spring.
Okay. Because like if you try to think about like just like a slinky just getting bigger and bigger and bigger off into infinity, that's how I'm trying to picture it.
Mm-hmm. Yep. Yeah, this would be like having when you drove your car over a bump, if your car flew into the air and kept going.
Okay.
Like, and worse yet, actually accelerated faster and faster as it.
Yeah.
I guess it would be, it's not the car and the bump that's the spring system, though. It's the car and the wheels that are the spring system.
Mm-hmm.
So this would be like if the wheels flew off and kept going.
Yeah.
Which would be kind of inconvenient.
Yeah.
Yeah, so one way you could describe this is this isn't a real spring, and the other way you would describe it is that it's anti-overdamped.
Yeah.
Which we could tell right here. The friction in this system is negative.
Okay.
Friction should be positive.
Should be positive. You're just writing these notes down here. So there actually is a way you can kind of just look at the differential equation itself and say, okay, wait a minute, the y prime term is plus or minus. That should be like your first clue.
Yeah, really what you're doing is you're doing this, right? You're using mass times acceleration, right? And I guess I shouldn't have a vector hat on that. is minus the frictive force times the velocity plus the spring constant. Minus the spring constant times the displacement.
Okay. Yeah, because velocity is just y prime. It's first derivative.
Yep, and the displacement is just y. So this really should boil down to my double prime is minus by prime minus ky.
Yep. Okay, that makes a lot more sense.
Yeah, and so after you move them to the other side, they should both have positive signs. If they don't both have positive signs, then either your spring constant, your spring actively wants to get the opposite of what it should.
Yeah.
Like it's not acting like a spring, or friction's not acting like friction.
Yeah. So if you were to do 4b, you can see 4y prime is positive. That's what friction should be.
Yep. Yeah. So looking at 4b, we have 4. Maybe let me just dump a eraser on this here. Oops, that's sort of light lime green. Weird. I wish the color picker on this thing would let you just input a hex value.
Yep.
Instead, you just get to point at it, and that often means that you get this. Now this is slightly lavender or something. Okay, so for the other problem there, we have 4y double prime plus 4y prime plus 1 y equals 0. And from this, we can look at the signs and go, okay, so positive and positive means that this thing actually is a spring. And I guess this thing also being positive.
Yeah.
So if all three things are positive, then this is some kind of actual honest spring. And so then I start thinking about, okay, so I have 4r squared plus 4r plus 1. And then I suppose equals 0. And then that, I think, factors into 2r plus 1 squared equals 0. And that would tell me that r is minus a half twice.
Okay.
And so that's going to be the repeated real roots case.
Mm-hmm.
Which tells me that I'm talking about something that's critically damped.
Okay.
Does that help a little bit?
Yep. And basically, 4c is basically 4a. You just have to rearrange the equation a bit, and you see, hey, wait a minute, y prime is negative. You're kind of in the same position as 4a.
Yep. Yeah, on that one you'll get two complex roots, but the real parts are positive, which means that you get something like this. Mm-hmm. Maybe let me just do that one instead of. Because anybody who watches this video is going to have no idea what I'm talking about unless I actually just... Oops, that's not helpful, Joe. Okay, so that one is y double prime equals 4y prime minus 13y.
Yep.
And already the fact that there's a minus 13 on the right-hand side... That's fine, but what about the 4? 4 should be negative when it's over there, right? So I, do a little algebra to this thing and get y double prime minus 4y prime plus 13y equals 0. And I think to myself, this is probably not really a spring because of that minus sign in there.
Yep.
But if I kind of fiddle with this thing, I get r squared minus 4r plus 13 equals 0, which I can complete this square on. That's r squared minus 4r plus 4 plus 9 equals 0.
Yep.
And that's r minus 2 squared equals negative 9.
Yep.
And so my r is 2 plus or minus 3i. And so that tells me my y's look like a e to the 2t cosine 3t plus b e to the 2t sine of 3t.
Yep.
And then the thing about this is that this tends to infinity as t tends to infinity, right?
Yep.
Okay, so this is anti because of this last part.
Mm-hmm.
And then because of the fact that I got complex numbers in there with a real part, this is anti-underdamped.
So the first one was anti-overdamped. This is anti-underdamped.
Yeah, so the distinction there is that an overdamped system does something like this.
Okay.
And an underdamped system does something like this.
Okay. It's like the waves just keep getting smaller and smaller.
Yeah, exactly.
Do the waves ever reach 0 though?
No, not mathematically.
Okay.
But they reach the engineering meets math answer to that is eventually they're so small that the oscillations due to the object's temperature are larger in magnitude.
Okay.
Or they reach the limit of our instrumentation pretty quickly.
Yep.
So it's not like mathematically it won't ever stop moving, but physically you won't be able to tell after not very long.
Yep.
Anything else on these?
Not on these, no, but I do have a couple more questions just in general.
Okay, let me pause this recording.